Points in 3D space, vectors for direction and movement, matrices for geometric data manipulation. Definition of points in 3D space. Example illustrations of points represented in 3D space. Importance of points in defining positions in a three-dimensional environment. Here's a simple example. Consider a room with three axes labeled X, Y, and Z. A point P in this room could be represented as 2, 3, 5. This means that the point P is located 2 units along the x-axis, 3 units along the y-axis, and 5 units along the z-axis from the origin, the point where all axes intersect. Illustrations of points in 3D space could include graphical representations where points are shown as dots or small spheres at their respective coordinates within a three-dimensional grid. These illustrations help visualize the spatial relationships between different points and their positions in the environment. Points play a fundamental role in defining positions in a three-dimensional environment because they serve as the basic building blocks for constructing shapes, objects, and structures. By specifying the coordinates of points, we can precisely locate and describe the positions of vertices, corners, and other key features in three-dimensional space. This is crucial in various fields such as architecture, engineering, computer graphics, physics, and more. When accurate spatial representation is essential for analysis, design, simulation, and visualization. Introduction to vectors. Definition of vectors and their significance in mathematics and computer graphics. Basic properties of vectors, magnitude, and direction. Explanation of how vectors are used to represent movement and direction in 3D space. Vectors are fundamental mathematical entities used to represent quantities that have both magnitude and direction in mathematics. A vector is typically denoted by an arrow, where the length of the arrow represents the magnitude of the vector, and the direction of the arrow indicates the direction of the vector. In computer graphics, vectors play a crucial role in representing various elements such as positions, velocities, forces, and directions. They are essential for describing objects' movements, transformations, and orientations in a three-dimensional 3D space. Here's how vectors are significant in mathematics and computer graphics. Magnitude and direction. The most basic properties of vectors are magnitude and direction. The magnitude of a vector represents its length or size, while the direction indicates the orientation of the vector in space. These properties are crucial for understanding and manipulating vectors in both mathematical and graphical contexts. Representation of movement and direction in 3D space. In computer graphics, 3D space is represented using a coordinate system, typically Cartesian coordinates. Each point in the space can be represented by a vector from the origin to the point. Vectors are used to describe movement and direction in the space. For example, position vectors. They represent the position of point in 3D space relative to the origin. Direction vectors. These indicate the direction in which an object is moving or facing. Velocity vectors. They represent the rate of change of position of an object in a particular direction. Force vectors, used to represent forces acting on objects in 3D space such as gravity, friction, or applied forces. Normal vectors. In computer graphics, normal vectors are crucial for shading and rendering, determining how light interacts with surfaces. Operations on vectors. In both mathematics and computer graphics, various operations can be performed on vectors such as addition, subtraction, scalar multiplication, dot product, cross product, and normalization. These operations allows for transformations, calculation or distances, angles, projections, and other manipulations essential for solving problems in both domains. Representing vectors. Illustration of vector representation using arrows. Explanation of vectors components x, y, and z. Examples of vectors representing various directions and magnitude. Vector representation using arrows is a visual way to depict quantities that have both magnitude and direction. In this representation, the length of the arrow indicates the magnitude of the vector, and the direction of the arrow indicates the direction of the vector. Let's break down the components. Number 1. Component of a vector. Magnitude length. Represents the size of or strength of the vector. Direction indicates the orientation or where the vector points in space. Number 2. Vector components. X component represents the magnitude of the vector in the horizontal direction, usually along the x-axis. Y component represents the magnitude of the vector in the vertical direction, usually along the y-axis. Z component represents the magnitude of the vector in the depth direction, usually along the z-axis. This is applicable in three-dimensional space. Number 3. Example of vector representation. Let's say we have a vector with components 2 or 3. This means it has a magnitude of 2 units in the x direction and 3 units in the y direction. So we draw an arrow starting from the origin 0, 0 and extending 2 units to the right, positive x direction, and 3 units upwards, positive y direction. Example 2. For a vector with components 1 to 4 means the vector points towards the left, negative x direction with the magnitude of 1 unit and downwards, negative y direction with the magnitude of units. So we draw an arrow starting from the origin and extending 1 unit to the left and 4 units downwards. Example 3. 3D vector. In three-dimensional space, let's consider a vector with components 1, 2, 3. This means the vectors as a magnitude of 1 unit along the axis, positive direction, negative 2 units along the y-axis, negative direction, and 3 units along the z-axis, positive direction. So we draw an arrow extending 1 unit to the right, 2 units downwards, and 3 units upwards from the origin. Vector separation. Addition and subtraction of vectors, scalar, multiplication and division, dot product and cross product. Practical applications of vector operations in 3D graphics and physics simulations. Vector operations are fundamental in various fields such as mathematics, physics, computer graphics, and engineering. Let's delve into each operation and its practical applications. Number 1. Addition and subtraction of vectors. Definition. When two vectors are added or subtracted, their corresponding components are added or subtracted respectively. Practical application. In 3D graphics, adding or subtracting vectors can be used to translate objects. For example, when moving a 3D object in a game environment, vectors are added to its position vector to represent movement in different directions. Scalar multiplication and division. Definition. Scalar multiplication involves multiplying each component of a vector by a scalar, a single numerical value. Scalar division is dividing each component of a vector by a scalar. Practical application. In physics simulations, scalar multiplication can be used to scale forces acting on objects. For example, increasing the gravitational force acting on an object by multiplying the gravitational acceleration vector by a scalar value. Dot product. Definition. Dot product of two vectors yields a scalar quantity equal to the product of the magnitudes of two vectors and the cosine of the angle between them. Practical application. In computer graphics, the dot product is used to determine the angle between two vectors, which is crucial for lighting calculation. It helps determine the intensity of light reflected of a surface based on the angle between the light source direction and the surface normal. Cross product. Definition. The cross product of two vectors yields a vector perpendicular to the plane containing the two original vectors. Its magnitude is equal to the area of the parallelogram formed by the two vectors, and its direction follows the right-hand rule. Practical application. In physics simulations and graphics computer, the product is used for various tasks such as calculating torque, determining orientation, and generating surfaces with normals for shading.